Okay, let's discuss another method for solving recurrence relation, that is called as master theorem. And under master theorem, like whatever recurrence relation we have seen, that is t of n equal to a into t of n by b plus f of n. So here we had either a constant or some function of n, that is why we can write it as a f of n. So what this says, again we have a problem of size n, which is divided into a number of sub problems of size n upon b, and the local computation time required to divide that problem of size n into a number of problems of size n by b is f of n. So f of n could be a constant or a function of n, constant or function of n. So now to solve the master theorem, we have three cases, and based on those three cases, just by looking at this recurrence relation, and based on the values of a, b, and one more value is there, like we have value a, b, and value c. So based on these three values, we can just find out under which case this recurrence relation falls. So let's see how it goes now. So let's see how it works. So see, we have function f of n. So if f of n is a constant c, or if it is a function of n, like just a n, or it could be n log n, or it could be n square. So what is this c indicates here? Like let me just say that this is constant k. Okay. So now if f of n is a constant k, now what this c indicates? So when by looking at f of n, if we write f of n, only the complexity of f of n in terms of big O we write. So it could be, we can write it as a big O of n to the power c. So now if you just compare the complexity of f of n with respect to big O of power n to this big O of n to the power c, then we can calculate that what is power of n is value of c. So now you can see here k is there, so I can write this term as k into n to the power 0. So now this will become big O of n to the power 0, that is k into n to the power 0. So k also will be there. Now what is c here then? This implies c equal to 0. So this implies c equal to 0. Then here you can see n to the power 1, so which will give us c equal to 1. Even you can see here n to the power 1 and then log n is there. So we'll just write n to the power 1, so I'll write c equal to 1. Now here n to the power 2, so I'll be getting c equal to 2. So the power of n is the value of c. So now we got c value, so we calculated c. Now based on again a and b, we have to calculate one more value, that I will just say that c critical is equal to log of a to the base b. So now whatever value of a and b are there, based on that I have to calculate c critical. Then, and most of this discussion I am following from Wikipedia, okay, and I felt this is really well structured, and they have just explained these all the three cases in tabular form, so that which will help us to understand what is master theorem. So I'll be following that whatever explanation on Wikipedia is there. I am just going through it, and based on that I am just trying to explain this. So now based on the values of c and c critical, we will be getting three cases. So now the case 1, so case 1 will be c is less than c critical. Okay, so if c is less than c critical and we have f of n complexity as big O of n to the power c, right? C is less than C critical and we have f of n complexity of big O of n to the power c, then T of n complexity is written as theta of n to the power c critical. Okay, so it is theta of n to the power c critical. That is what our case 1. So if c is less than c critical, then the complexity of T of n is theta of n to the power c into c critical. Then I will go to the case number 3, the third case, which is c is greater than c critical. Even we can have it is as a second case, not a problem, but we'll just follow the same. So c is greater than c critical. Then in this case, what will happen is f of n might be having some power which is like c has very higher value and c critical has lower value. So f of n, we don't need to compute the complexity of f of n in this case. We can just directly write the complexity of T of n as theta of f of n. So whatever f of n is there, that f of n is written as its complexity of T of n. So what these two cases indicate, you can just see when I calculate what this A indicates number of sub problems. So what I am saying is the local computation time, whatever local computation time we will be getting, how much that time is required, like how much time is required to divide a problem of size n into a number of sub problems of size n by b. So when I am taking log of a to the base b, in that case I will be getting some value of c critical, and if this value is little bit higher, what this indicates, my number of sub problems, like number of sub problems are more. So I have one root, and for that root I have more number of sub problems. You can just look into this. So your recursion tree may look something like this. So now in this recursion tree, what will happen? We have number of leaves are more. Okay. So now in this more number of leaves, again, like let's say again here also I have some problems. So now in this more number of leaves, what will happen is this tree will look like a leaf heavy tree. So in recursion tree, when you do, the first case is leaf heavy tree. In second case, what will happen? C is greater than C critical, where we have written. So what this means, the log of a to the base b value is little bit lower compared to the value of C what we have. In that case, what will happen? You have more number of roots than leaf. So your tree may be something like this, just one-sided tree. So we have more number of roots in this case instead of leaves. So these are the two cases, and the case number 2, as we discussed, will be obviously C equal to C critical. But now again, under this C equal to C critical, we have one crux. Like what we have to do is, whatever f of n is there, instead of representing its complexity big O of n to the power c, we have to write it like this: big O of n to the power c into log n, and log n's power should be k. Okay, so now f of n is big O of log n to the power c and log n to the power k. So even if you have only n, what will happen? F of n equal to n. Then how you can write this? It is n to the power 1 into log of n to the power 0. So what is the value of k? K equal to 0 in this case. So now based on this value of k, we have again, based on the k, we have 3 sub cases for this case of master theorem. And what are the 3 sub cases? Again, k is greater than or equal to -1, or k equal to -1, or k less than -1. Okay, so we'll discuss all these cases in subsequent videos.